Hello and welcome to this calculus video. Today we'll be talking about taking a limit at infinity.
Math 112.
Let's have a look at these three examples. These functions are all different, but as x becomes very large, the corresponding y values all begin to approach 1. It is this behavior that we are interested in today. Now let's state the formal definition of the limit at infinity. Let f of x be a function whose domain contains some interval a to infinity. Then the limit as x approaches infinity of f of x equals L means that the value of f of x can be made arbitrarily close to L by making x sufficiently large. There is also a similar definition for the limit at negative infinity. Can you work out what it should be? So now we know what limits at infinity are, but how do we compute them? One reasonable strategy for computing standard limits is to attempt to plug in the limiting value. If nothing goes wrong, like dividing by 0, and our function is continuous, then we are done. If our plug-in strategy doesn't work, we often perform some algebraic manipulations on the function, and then try plugging in. We can't do the same with limits at infinity though, because we can't plug infinity into expressions and do arithmetic. As we see here, trying to do arithmetic with expressions involving infinity can lead us to inconsistencies, so we have to do something else. Let's have a look at this rational function. If we try plugging in infinity, we will get nonsense. So instead, we are going to have to modify this function first by dividing top and bottom by x squared. Our new expression is equal to our old expression, except when x equals 0. So the limit at infinity will be the same. Now, the limit as x approaches infinity can be read off as 2/3. Why does plugging in infinity work now? Well, the thing that causes problems with infinity are indeterminate forms, which are expressions where the value is ambiguous. Let's compare infinity plus infinity with infinity minus infinity. The first expression is unambiguously infinity, but the second expression is ambiguous. The natural inclination to cancel the infinities and get 0 is invalid, because the function x plus 1 minus x, when you take the limit, is not equal to 0, even though you get something in the form infinity minus infinity. As a rule of thumb, if you are trying to subtract infinity from infinity or divide infinity by infinity, the quantity is ambiguous, so you should try to do some algebra on your function first to remove this ambiguity. One last thing before we are done. There is a very close connection between horizontal asymptotes and the limit at infinities. If either the limit as x approaches infinity or negative infinity of f of x is L, then the line y equals L is a horizontal asymptote of the function f of x. That's all for now, folks. Today we discussed limits at infinity, we defined what it means for a function to have a limit at infinity, and we talked about some pitfalls and strategies for computing them. We also observed that there is a correspondence between horizontal asymptotes and limits at infinity.
Math 112.